So electromagnetic induction is our chapter. We are doing the magnetic flux, the first thing, represented by phi. And for magnetic field, I'm going to write B, phi B. How do we define that? The number of field lines, magnetic field lines passing perpendicular through a surface. This is the statement. Number of magnetic field lines passing perpendicular through a surface. This is the surface. Then whatever field lines are passing perpendicular to that, that's a magnetic field we are having. So the flux value will be what? What do you think? Since only 3 magnetic field lines are passing here, so magnetic field flux value will be 3. Number of field lines passing perpendicular to the surface. So how we calculate that? Okay, it's very easy. We observe one thing. The phi magnetic field flux value, phi B, is directly proportional to the strength of magnetic field. Why? Because greater the value of the strength of magnetic field, denser are the magnetic field lines. More lines will be passing through your plane. This is what you want for a greater magnetic flux. So flux is directly proportional to the strength of magnetic field B. Because higher the value of B, denser are the lines, more lines are passing, B value is higher, phi value is higher. Also, greater is the surface area of your plane. Surface area is bigger, more lines can pass through it. So that will also increase your phi value, flux value. Area. Okay, we can understand the concept from electric flux also. There also it was happening. For okay, if you combine these both, see one thing. First equation and second equation. Phi B equals B naught.
So is that fine if I write phi m or which one?
Okay, you can write phi M also, but NCERT does not show it with M. It shows magnetic field with capital B. So always show the magnetic field with B and electric field with E. We got this here. So magnetic flux mathematically is the dot product of the magnetic field vector and the area vector through which the magnetic field lines are passing. You will open it up. So phi B equals BA cos theta, which tells us something specific that we have already told in the definition: perpendicular lines. Be more clear in this. This is the surface I am having of A area vector. The area vector is like this, but the field lines are not perpendicular. I'm making an angle with the area vector. They don't seem perpendicular. They are making a theta angle, for example. So definition says the number. So what number of magnetic field lines? Only those number of magnetic field lines are passing perpendicular, not a theta angle. It should be 90 degree. That's for sure. So in the formula, you have taken that particular magnetic field lines which are perpendicular. B cos theta. B cos theta are the magnetic field lines which are perpendicular to the surface. B is that thing. B cos theta is that component. Or you can say area vector should be perpendicular to the magnetic field. So we have taken that particular area vector which is along the magnetic field lines. A cos theta.
So in that one, it's showing the A and B are aligned now. That
So
the cos series one. Okay.
perpendicular to the plane, but area vector and B will be aligned. Different thing. Okay. So we got the formula finally here that flux of magnetic field equals dot product of B vector and A vector, which is BA cos theta. You can write either way, AB cos theta or BA cos theta. And dot product of two vector gives us a scalar. This is why flux is a scalar quantity. What will be the unit of that? So the unit of magnetic field is Tesla. Area is meter square. So Tesla meter square, which is also known as Weber. W-E-B-E-R. Weber. Represented by capital W. Magnetic flux is represented. The unit of magnetic flux is Weber. W-E-B-E-R. Represented by capital W. Okay. Now come the Faraday. Faraday's experimental observation. In order to understand the Faraday's experiment, with which usually the chapter starts, we should have the prior knowledge of magnetic flux. This is why we have already discussed about the flux. Now we understand flux, we are good to understand the Faraday's experiment also. Faraday's experimental observation. What were his observations? So Faraday observed that, first thing, current is induced. You don't know from where. Don't write it. Okay. It was induced without any kind of touch, because we need conduction. But there was no conduction. Even then, the current is being induced. In what? In a coil which is conducting. A coil of area A. When the coil was placed in magnetic field, if I conclude, then Faraday was doing something, and he observed that all of a sudden, if a coil is kept in a magnetic field B and the area of coil is A, then he observed the deflection in galvanometer of the coil. Okay. Some current was induced for a moment out of nowhere. He was doing some other experiment. He accidentally figured it out. He was doing what? He was having a solenoid kind of thing, and he was figuring out something else. And then out of frustration, he did what? He threw a wire or something, a coil, and the coil passed through the magnetic field. And when it is moving, the coil is changing its position, its flux is changing, and somehow he shows that the current is passing through the coil. He was not intended to discover the electromagnetic induction. Faraday was the guy who invented it, discovered it. You know the difference of invention and discovering something?
Actually, that's when you make something new and discover it.
Yeah. Okay. So this is for sure. Okay. When a coil is there of area A, if kept in a magnetic field B, I current is induced somehow. But only in three conditions I was induced, not always. What were the three conditions? This is what you need to write. First condition is B is non-uniform. It's not that you are having a magnetic field flowing left to right and you keep a coil in between that and then you will see your bulb lighting up. No, it won't happen. Only in three conditions your bulb in the coil will light up. The first condition is B is non-uniform. That means it's time dependent. B equals 2t or something like this. Okay. B is changing as per time. Yeah, it's not constant. In that case, it happens. Current is induced. For example, you are having an inward magnetic field, which is variable, and you kept a coil in it. Then you see there is a current I induced. There's a reason I have drawn the current direction like this. We'll discuss that later. Okay, first thing was this, when B is changing somehow. Second condition he observed was when area of the coil is changing. The coil is getting bigger and smaller in size, bigger and smaller in size. Area of coil is changing. Magnetic field. Coil is kept, which is growing in size, getting smaller in size. Current was induced. I. If you observe something that the inducing current, okay, it is doing what? It is going to produce a magnetic field of itself, induced magnetic field. There is a current in a coil, definitely there's going to be a magnetic field due to the current. That magnetic field is going to be the direction opposite to the source magnetic field. If you use your right hand palm rule, my source magnetic field was inside, but the resultant magnetic field, a new magnetic field, the induced magnetic field, is outside. In such a direction, my current is induced, that the magnetic field induced should be opposite in the direction of the source magnetic field. Just an observation. We'll talk about this enough after a while. Okay. Third thing that he observed was theta is changing. Theta is what? Theta is the angle between magnetic field and the area vector of the coil. Theta is changing. How can it change? So you are having a magnetic field, but this time your coil is rotating somehow. Like this. This is the axis of rotation of the coil. Coil is just rotating somehow. If it is happening, so it is continuously changing the theta, because area vector is continuously changing. B is fixed inside, but area vector is continuously changing. That means theta is changing. If it is happening, then also a current induced was observed in this particular direction. If I conclude or summarize that all, so in three conditions current was induced. First was B is changing, second was A is changing of the coil, third was theta was changing, right?
Sir,
Yeah.
it's in the diagram, what if the magnetic lines are going vertically upwards and count as cutting on?
Magnetic field lines are,
Like it's rubbing into the page. Could you reply?
see, the condition is magnetic field lines should pass through the coil, and then the theta should change.
So it won't count as passing.
Yeah, it won't count in flux if it is not passing through it, right? It has to pass through the coil. So if you summarize that all, if B, A and theta is changing, you say there is a induced current. If not, there is no induced current. If you just keep a coil, do nothing, no current is induced. These three, either of the three condition or all the three condition, at least one of it should be there, then your current will be induced out of nowhere. It was quite of magical thing for those days. Without a battery, current is getting induced. So we have seen I is induced out of three conditions. B is changing, area is changing, or theta is changing. And you combine that and you say if either of three changes, that means flux has to change. Magnetic flux has to change, because magnetic flux equals what? BA cos theta. It includes these three. If either of one, like any changes, B changes, A changes, theta changes, flux will change definitely. So why do I say B or A or theta separately? Let's say if flux changes, current is induced. That is the condition of Faraday. Okay. So it was an experimental observation of Faraday. Now comes the Faraday's law. New heading. He did the experiment, he observed something. Now we'll see his law. Let me know once it's all done.
Yeah.
Faraday's law. The first law is Faraday's first law, obviously. We call it Faraday's first law of electromagnetic induction, in short, EMI. Shall I say the statement? whenever there is a change in magnetic flux linked with a conductor, comma, and EMF is induced in the conductor, and EMF is induced in the conductor, full stop. The statement is whenever there is a change in the magnetic flux linked with the conductor, those flux which is associated with the conductor of the coil, and EMF, I'm not saying EMI, EMF is induced. EMF is voltage potential, if you know, right? Electromotive force. It is going to driven or force the electrons to move, which is what potential also does. So EMF is potential also. Okay. And if a conductor forms a closed loop and induced current flows through it. Next slide.
Next.
No, it's not it's the first law, second statement of the first law. If the conductor forms a closed loop or coil and induced current flows through it. There's a reason why I'm saying this. If the conductor forms a closed coil or a loop and induced current flows through it. You said you keep a conductor, any of any shape. If flux linked with it changes, varies, EMF is induced first of all. But current only flows when there is a closed loop, right? So if you're having a bar placed like this in a magnetic field, if flux through the bar is changing, definitely EMF is induced, but no current. There is no induced current. For induced current, you need a closed path. You form a circuit for flowing a current. So EMF is there, but no current this time. If flux is changing. Okay. If the conductor forms a closed loop like this, then first of all comes EMF, potential difference, electromotive force, which is going to drive the electrons in the coil. Okay, when electrons drive and then the direction opposite, current flows in this direction. In this one, in the case of bar, there was no path for the electrons to flow, and this is why there is no current, only EMF. Condition is flux should be changing. Okay. The Faraday's first law can also be expressed in this way. I'm going to draw. This was the thing. There is a coil. Faraday was working like this in his laboratory. A circuit was there. There is no battery in the circuit, but there was a galvanometer here. And nothing was happening. See, there is a bulb. In the place of galvanometer, you can put a bulb. Faraday had some device here which shows indication. He might have a bulb there. So nothing should happen. The bulb or the galvanometer here should not be light enough for any instant. There is no current right now. But he accidentally threw a magnet, a bar magnet. Which fortunately passed through the loop of this coil, of the circuit. And as the bar magnet passed through it, and bar magnet is what? A source of magnetic field. So if bar magnet is moving, that means magnetic field is changing through the coil. For that particular instance, see, three magnetic field lines are passing now. If you see if bar magnet is kept here, a greater number of magnetic field lines are passing through the loop now. There is a greater coverage. Okay. As it goes far away, field lines goes to zero. Field is continuously changing. You get it? So the moment he threw it, he observed there was a sudden blink in the bulb. In the place of galvanometer, there was a bulb at that time. It blinked. for his surprise. It was quite magical. Then he did the thing again. The bulb blinked again. Then he did his experiment to find out what is causing it to happen. The changing B, the changing A, or the theta. This time B is changing, as you can see. Or you can say phi B is changing. This is also a way of understanding the Faraday's first law. So it was observed when the magnet is brought closer to the coil and then it moved away. When closer to the coil, phi is bigger. When moved away, phi is less. So phi is changing continuously, getting bigger and smaller. Induced current was observed in the galvanometer, which tells us whenever there is a relative motion between the coil and magnet, an EMF is induced in the coil. If the loop is closed, an induced current flows through it. You just make yourself a little more wiser when you say when the loop is closed, current also flows. But in the statement of Faraday, it was only EMF. See why I have said relative motion. If there is a relative motion between the coil and bar magnet, then current will be induced.
Yeah, I got it.
Yeah. So relative motion is the key thing here. See, if the coil and bar magnet both are moving with the same speed, the relative motion is zero. In that case, you will not see any induced current. Right? This is why I have said relative motion. The motion should be relative between the coil and the bar magnet. One more thing, the induced EMF. Okay, right now the source thing is EMF, because when comes EMF first, only then current is induced. So I'm just saying EMF now, induced EMF. The induced EMF lasts as long as the change in flux is taking place. The moment flux stops changing, EMF is gone. Right? Nothing will happen. This was all about the Faraday's first law of electromagnetic induction. Why do I say electromagnetic induction? Induction is getting induced without any touch. Okay, induction is getting absorbed without any touch. Conduction is getting absorbed with the touch. So electromagnetic induction. Due to the magnetism, electric field is getting induced. But due to the magnetism, due to the electric field, magnetism is getting induced. Both the way it works. We'll see that later. Right now, magnetic field is inducing the electric field. If there is a current, there should be electric field also, right? Somehow, there induce a EMF, then induce a electric field. Electric field pushes the electron, then pushes a current. So, electric field is also induced, EMF is also induced, current is also induced at the same time. Okay. Now comes Faraday's second law of EMI, electromagnetic induction. The statement is, see, the laws are written in the same statement. Newton's laws also. Okay. Faraday's laws also. It's better to write these laws in the same statement they have given to us. Law is, the magnitude of induced EMF is directly proportional to the rate of change in magnetic flux. Induced EMF is directly proportional to rate of change in magnetic flux. Okay, I'm not saying it is directly proportional to the change in magnetic flux. I'm saying it is directly proportional to the rate of change in magnetic flux. How faster you are changing. You're changing it, it's good. But if you keep the change same, okay, it won't do any good. You have to, like, either you are increasing the magnetic field to a greater amount or you are decreasing it to the greater amount. Both the cases, higher EMF will be induced. Okay, the speed of changing should be higher, not just changing. Speed of changing should be higher, or can be low also. Change can be increasing and decreasing both.
So if my rate of change of flux, so my initially let's say my flux is 5 meters. induce EMF, right? Or it won't be.
So what I'm saying is, along with flux, there is a time axis also in order to induce a EMF. Why time axis? You are making a change, right? The change should keep happening. Right? You have made a change once, but you have to make the change along with the time. Time is running forward. The change should also happen with the time. You get my point? This is why I'm saying rate of change, not just change.
Rate of change.
Rate of change.
Okay. So like, what is this like analogous to velocity, like rate of change, position, I say
Velocity is the rate of change of
position.
position, distance.
So is it like that or is it like acceleration?
No, it's not acceleration. It's like velocity. Okay. The symbol of EMF, induced EMF, is a small e, or with the epsilon you can show it like this. I'm going to use a small e. Okay. Induced EMF for small e. So, according to the second law of Faraday, E is directly proportional to the rate of change in electric flux. Delta phi over delta t. The proportionality constant comes out to be 1, and you can simply write here that E equals delta phi over delta t. If we are talking about the average EMF which is induced, then do this. Instantaneous EMF you are finding at a particular instant of time, it will be obviously d phi over dt. Okay, I have only accounted the magnitude this time because we don't worry about sign for finding EMF, potential difference. Okay, it works without sign. We are dealing with this way, right? EMF is potential only, and this is why I don't show any kind of sign, positive or negative, but in real the formula is E instantaneous equals negative d phi over dt, or E average equals negative delta phi over delta t. There is a great significance of negative sign. Okay, keep that with yourself. Or you already know about it.
What's the minus for again?
The minus sign, okay, you have seen I was drawing the current in a particular direction, the loops,
Oh yeah, it's in the opposite direction.
opposite direction. So this EMF is inducing it's coming from somewhere. This phi is the source. The field was already there. Phi is coming out from there. So this EMF, the induced thing, on these both factors are opposite to each other. We will talk about that in Lenz law later. And now what is E? So E is EMF. We have talked enough about the EMF, electromotive force. Let's talk about the induced current. In second law only, there is no new heading. Induced current. Induced current I. Taking the resistance of the coil be R, small r. Then the formula of I average current, will obviously be E average over time. Okay, it should be E average over R. I equals B over R, right? Potential over resistance. Make sense? E average formula is delta phi over delta t, which gives us times inverse R. This was the formula of I average, delta phi over delta t times 1 over R. I instantaneous in the same way will be d phi over dt times inverse R. All right. There's a question.
So,
Yes,
yeah,
say.
so I'm gonna ask questions about it like I instantaneous equal to d by dt.
I instantaneous equals d phi by dt times 1 over r. Yeah,
Why do we need the negative sign?
you can keep the negative sign, but have you ever like you don't really write current with the negative value. You don't write potential with the negative value. You can just simply show that in the diagram, right?
So like just for direction.
The direction thing. It only tells you the direction of current. Since B was negative, see, the real formula was negative d phi over dt, which will also give you negative d. The I instantaneous will be what? Negative d phi over dt times 1 over r, which obviously tells you current will be induced in such a direction which is going to oppose the source magnetic field, which is also Lenz law. So now there is the question. Just simply remember the value of E, d phi over dt. Everything else is completely known. And E is the analogous for potential difference. If the magnetic flux phi B equals 5t square plus 4t plus 1, it's completely time variable, full stop. Find the induced EMF, find small e, through the coil at,
Plus 4.
find the induced EMF through the coil at t equals 1 second. It's a instantaneous current, instantaneous EMF. 1 t equals 1 second.
Yes, it's 14. 14 PM square.
So it's what?
14.
14 volts.
Yeah.
14 volts, because when you will differentiate that, you'll get 10t plus 4,
Yeah. And then
and the unit is volts. Bever per second is giving you what? Volts. Bever per flux, t per second, right? So Weber per second is the volts. The unit of EMF will be volts only. Okay. New question. Let me know once you have written it.
yeah.
Okay. A coil is placed. A coil is placed with its plane perpendicular to the uniform magnetic field, of strength 0.5 Tesla. Of strength 0.5 Tesla. Full stop. If suddenly the radius of the coil starts shrinking with the rate of 0.1 mm per second. Full stop. Find the EMF induced in the conducting circular coil. Find the induced EMF in the conducting circular coil, comma, when the radius of the coil is 5 centimeter. In conducting circular coil, comma, when radius of coil is 5 centimeter. This time I have not given you direct Weber equation, the flux equation. I have given you what? Area relation. Area is changing at the rate of 0.1 mm per second, and since it's shrinking, so negative 0.1 mm per second.
0.1 okay. 0.01 mm square. So 0.01
Okay, so the answer should be 0.5 pi times 10 to the power minus 4. 0.5 pi times 10 to the power. Let me know once you get the answer. See, for finding the EMF, which the question is also asking, finding EMF, the only formula we know is d phi over dt. If we don't know d phi over dt, then somehow we are going to find d phi over dt by using something else, which is area. Area is changing. So you got this? The answer? Yeah.
Oh, yeah.
Okay, now we have completely understood how to find the value of EMF. If you get the value of EMF, if you know the resistance, you can find the current also. It's possible, right? If it's not a loop, there's not going to be any current. See, I was drawing the diagram, so I was writing the current direction by myself, which is quite confusing. So we need something that we can find direction of the current also. It's a loop.
0.5
Yeah, it should be bold. So finding the value is very easy. Now we should know the direction of the induced EMF or the current. Right? New heading is direction of induced EMF or current. In brackets you can write Lenz law. Lenz was a scientist who gave it this particular way of finding a direction of induced current. Lenz law. The statement is, see, Faraday's laws are done, I think, for now at least. The statement of Lenz is the direction of induced EMF is always such that it opposes the cause producing it. The direction of induced EMF is always such that it opposes the cause producing it. So what is the cause producing it? If it is the changing magnetic field, okay, if it is the area vector, if it is anything else, the direction will be such for the current that will produce such a magnetic field which is going to oppose the cause producing it. If the coil is turning, direction will be induced in such a direction, then the coil will wants to turn in another direction due to its own magnetic field which is induced later. The statement, just remember statement 1. We'll talk about that in detail now. Is it done? Okay. So let's see an example for that. We are having a inward increasing magnetic field. And a loop. Okay. So current will definitely be induced when I'm saying that B is increasing continuously. If B is increasing, Means flux is changing through the coil. Current should induce, theoretically. What is the direction of the induced current? So current will induce in the given coil, but we are determining a direction. The Lenz law is telling us the current will induce in such a direction that is going to oppose the cause. The cause is increasing magnetic field, right? The cause is the inward magnetic field, inward. So if you check, direction should be such that magnetic field which is inward should be opposed. And how will it be opposed? If current flows in this direction. I can check with your right hand thumb rule. The magnetic field lines due to the induced current, because when a current passes through a loop, it produces magnetic field. Two things are happening. The inward magnetic field is inducing the current. Now when the current is already induced, now this induced current is going to produce a new magnetic field. Now what I'm saying is the induced current, the new current which is there magically, will induce such a magnetic field line, which will produce such a magnetic field line which is going to oppose the source magnetic field. Source magnetic field is inward. So current has two options. Either it produces a magnetic field inward or outward, but it is going to choose the opposite one, outward. And this is why current will take a direction of in the loop to flow in such a way that the magnetic field which will be produced will be outward. Yeah. Let me know if it's clear or I can explain it better. Okay, so if I explain it in another way, I can say current I will definitely be induced, but either it can be in the first direction I'm representing over this arrow, or it can be in clockwise direction in second way. What way it is going to choose? This is the question. You have to choose first arrow or second arrow for the current direction to flow. So if the current is I1, hypothetically I'm saying current is definitely induced I current, but either it is going to flow in I1 way or I2 way. So if current is I2, for example, so check the direction of magnetic field due to I2. You see, due to the I2 thing, the current is inward. Again, the magnetic field is inward. Magnetic field which will be induced is inward, isn't it? Due to I2 and due to I1, we check the direction of magnetic field. Due to I1, magnetic field will be outward. And Lenz law says current will be induced in such a way that it opposes it. So which one is opposing it? I1 or I2? I1, obviously. I1 is outward. I1's magnetic field is outward. I2's magnetic field is inward, which is the direction of the source magnetic field. But Lenz law says it has to oppose it. It has to be in the opposite direction. Source one is inward. New magnetic field, the induced magnetic field should be outward. This is why I2 is wrong. Current will be induced in I1 way only. Clear? Okay. Now you want to tell me? All right. At this time, if the magnetic field is outward, right? What way the current will be induced in the loop? Clockwise or anti-clockwise?
Okay, so it's going into, so source one is going into.
Outward. The source one is outward. So coming out from the screen.
It's coming out.
Yes, coming out. Magnetic field lines are coming out. Okay, so it's dots. P is changing and also outward. So what direction?
So then the current is induced and we need the magnetic field to be inside. So our current is going
Clockwise. Very good. So induced current direction is clockwise.
Yeah.
Good. All right. One more representation to that. If you are having a loop like this, and we are having a wire here, in which current is flowing in this way, and not a constant current, an increasing current, because only an increasing current is going to produce a variable magnetic field. Okay, increasing current is there. Tell me what direction of current will be induced in the loop, clockwise or anti-clockwise?
induced. So here so in the square.
Source field is going inward or outward?
Let's see. So I call it and then it will come out of the screen.
Okay, source one is coming out. So what should be the direction of induced current?
The induced current. So that we want the induced field to be inside. So it should be clockwise.
Clockwise. Good. Okay. One more. This is my current this time, and current is decreasing. And we are having a loop here. Now this time, what is the direction of current? Clockwise or anti-clockwise? See it? Check it out again.
Okay. So okay, we have excess. So it's going into the screen. So then we want something which will be dots. And yeah, so it will go
Okay, it should be anti-clockwise. Yeah, only then it is going to be outward. So anti-clockwise. Good. Okay, let's change the arrangement this time. And we are having a wire like this. Current is constant this time. What I'm doing is I'm having a loop. And loop is moving with the velocity v in this direction. Find the direction of the induced current. Loop is moving to the right.
relation meaning that is an increasing decreasing.
See, the current is constant. Okay.
Yeah.
You don't really need for direction. You see, if the loop is moving, there is a relative motion with the magnetic field and the loop that should be there for the induced current. The induced current will be there. Okay. You have to find a direction only. For direction, once you get direction of the source magnetic field, you can find the induced current direction also. For finding direction, you only have to find direction of source magnetic field. That's it. You don't require anything else.
Yeah.
So current is induced in what way? Clockwise or anti-clockwise? Yeah. Yeah, anti-clockwise. It's clockwise, anti-clockwise.
Even if it was moving closer, it doesn't matter.
It doesn't matter. It's changing, that's for sure, since loop is moving. Because magnetic field lines will be, the magnetic field strength will be higher in the proximity of the wire. As you go farther, magnetic field is decreasing. So flux is decreasing continuously as it going more to the right. Okay. You can see one more arrangement for that. Yeah. Okay, tell me this one. I current constant. There is a loop moving with the v velocity upward. What is the I direction? Yeah, there will not be any induced
Yeah.
current because
It's not magnetic.
yeah, there is no magnetic flux changing this time. You're only moving it forward.
But it's at the same distance.
Yeah. Okay. So no induced EMF this time. So we have to see the arrangement also. Okay, one last. Okay, so now we are having this inward magnetic fields. Source magnetic field is inward. Initially at time equals 0. Okay, at the starting. The loop was half inside and half outside. Like this. This is the termination point of the field. And at time equals t, then loop is completely inside. Like this. Moving to the right with the v speed. The direction of induced current. Find it out.
Clockwise.
Think about it. At t instant, what is the direction of current?
At t instant.
Yeah.
None.
So there is no induced current, right? During the journey, there is. But the moment, okay, the moment it covers itself fully in the magnetic field, at this moment, I'm going to draw it with the dead dash loop. Now there is a EMF at this point of time. The moment it moves a bit like to the right, the current vanishes. There is no current because area, the exposed area, okay, for magnetic field is not changing, it's constant. Same number of magnetic field lines are passing this time. Okay, why there was a EMF induced at this time? Because magnetic field lines were half this time and now it's full, but it's keep on like it's full only during the journey, when as long as it's inside the magnet, so it's not changing. EMF is 0, right? But at this instant, the dead dash I have drawn loop, at this point, what is going to be the direction?
The final.
No, the final one is obviously 0. In this one, I equals 0. So in this one, the dead dash I have drawn, the lighter one I have drawn, the moment it gets the full exposure of the magnetic field. Now there is a induced EMF, but after it, it won't have it.
So it's going inside. So clockwise.
It's going inside, so the
Clockwise.
it
So
should-
it also moves.
anti-clockwise. So current will be induced anti-clockwise. Okay,
Okay.
let's see one more. This is our loop this time, and I'm gonna drop a bar magnet from the top. Bar magnet is, this is the north pole, that's the south pole. What is going to be the direction of current? Clockwise or anti-clockwise?
Is it? It's not. Is it moving?
Yeah, I have dropped it.
Oh, you're dropping.
So the moment it's passing through the loop,
Okay. Clockwise.
clockwise,
It's from the top. No, opposite.
anti-clockwise, because we have talked about it. We want to get the south pole this at this time. South pole. So the source. Okay, we want to get the south pole or north pole. No, we want the north pole this time. Yeah, north pole goes like this. Let me check. If the north pole, so magnetic field lines are going inward. We want the magnetic field lines to go outward, which is only possible when the current is flowing outward. When the current is flowing anti-clockwise, you're right. Okay. Right? Yeah, because we want to get this particular formation which is possible at this way. This is north. And when you draw south, south is like this. Okay, what if I'm not dropping it this time, I'm pulling it up, the magnet.
The field doesn't change. Still same.
I have changed the field now. So it's south pole, it's north pole. Yeah, now I'm pulling it up. So don't worry about the value of if the magnetic field increasing or decreasing, only worry about the change. Okay, so source magnetic field. Source magnetic field is going inward, going outward this time, right?
Opposite.
Yeah. So it's going, the source is going upward. You want to get the magnetic field which goes inward, which is only possible with the clockwise, right?
Yeah.
The current will be induced clockwise. I think it's enough. Okay. All right. So we are meeting. It's, yeah, okay. So it was the pending class. We are waiting on Tuesday.